If we have more than one connection going out to the internet from our enterprise, instead of using a static route, a better approach might be to use BGP, Border Gateway Protocol. That's going to be the focus of this lesson, taking a look at some of the fundamentals of BGP. BGP is considered to be an exterior gateway protocol, an EGP. That's as opposed to protocols like OSPF and EIGRP, which are considered to be IGPs, interior gateway protocols. And BGP has some similarities and some differences with these interior gateway protocols. One similarity is that BGP does form neighborships with other routers. However, we can set things up such that those neighbors do not have to be adjacent to us. We might form a neighborship with a router that is several hops away. There's an option to do that. However, something that's different than OSPF or EIGRP, with BGP, we do not dynamically learn a neighbor. There is no automatic discovery of neighbors via multicast. Instead, we have to explicitly configure our neighbors. And once we've done that explicit configuration, when we form a neighborship, there's actually a TCP session that's established between those neighbors. And when BGP sends an advertisement, it's advertising the network address prefix and also the length. It's including subnet information, in other words. And this information about the address prefix and length, there's a term for that in BGP. It's called NLRI, Network Layer Reachability Information. And that's similar to OSPF and EIGRP because those protocols, they can send network address information, including subnet information. But BGP, in addition to sending address information, is also going to send a collection of path attributes, or sometimes we call those PAs. These path attributes can be used for path selection. If you think about OSPF, it has a metric, and that metric is used for OSPF to make its path selection. EIGRP has a metric, and we talked about the different metric components of EIGRP, but with BGP, we have a collection of criteria on which we could base our path selection. And in the upcoming lessons, primarily in the next module, we're going to see exactly how BGP makes its path selection decision and how we can influence that decision. And when we talked about OSPF and EIGRP, remember that we classified OSPF as a link state routing protocol, and EIGRP was an advanced distance vector routing protocol. Well, what is BGP? BGP is considered to be a path vector routing protocol, which is similar to a distance vector. Remember the routing protocol RIP? That's a distance vector routing protocol, and it can know that a certain network is available in this direction, and that destination network is a certain number of hops away. And with BGP, we can also know that a network is available in a particular direction, but instead of counting the number of router hops to that destination, BGP counts the number of autonomous system hops. We say that an autonomous system is a network under a single administrative control. Consider this topology. This is the primary topology that we're going to be working with in our BGP discussion. And notice that we have 4 different autonomous systems. Let's imagine that routers R1 and R2 are part of an enterprise network. They're under a single administrative control. They both belong to Autonomous System 65001. We've got a couple of ISPs. ISP1, that router belongs to Autonomous System 65002, and ISP2, that router, it belongs to Autonomous System 65004, and I put another router in the middle to represent all other routers on the internet. I call it the INET router. It belongs to Autonomous System 65003, and I created a loopback interface on the INET router to represent just some network out on the internet that we might be trying to reach from the enterprise. Let's go out to a live interface right now and see how we can connect our enterprise network using BGP out to a couple of different service providers on the internet. Let's take a look at how we can configure our enterprise. We're pretending that our enterprise is made up of routers R1 and R2. How we can configure our enterprise to connect out to the internet. We've got a couple of ISPs represented by routers ISP1 and ISP2, and I've got another router in the middle, the INET router, that's representative of all the other routers in the internet, and I've created a loopback interface on the INET router with an IP address of 9.9.9.9 with a 32-bit subnet mask, and we'll want to make sure that that network, which is representing just a typical network out on the internet, we'll want to make sure that that network is appearing in the BGP tables in our enterprise. And we're just going to configure routers R1 and R2. The other routers are already configured. This is very real world. In the real world, we would not be configuring the ISP routers. We're just configuring our routers. Let's begin on router R1. Here's how we set up BGP. We say router, BGP, and we give the autonomous system number. Notice from the diagram that we are in Autonomous System 65001. And if I have IP addressing assigned to a loopback interface BGP can use that as the router ID, and if I don't have that, if I have an IP address assigned to a physical interface, BGP can use that as a router ID. To make things easy to visualize for us, let's statically configure a router ID. I want to have a router ID of 1.1.1.1 on R1 and a router ID of 2.2.2.2 on router R2. To statically set the router ID, I'm going to say BGP router-ID, and I'll enter 1.1.1.1. What network do I want to advertise via BGP? In other words, what interface do I want to be participating in the BGP routing process? Well, in this topology, router R1 only has one interface that we see. It's Fast Ethernet 0/0, and it's part of the 192.0.2.0/24 network. Let's give the network statement to say that we want Fast Ethernet 0/0 to participate in the BGP process. To do that, we can say network 192.0.2.0. And notice from context-sensitive help that I could specify a mask if I wanted to give a subnet mask. There's not a need for me to do that in this case, though, because notice the first octet in this network address is 192. This is a Class C network, and we're using a 24-bit mask. That's the classful mask, and that's the mask that will be applied by default anyway. And as a result, there's no need for me to specify a mask. Something that's somewhat unique about BGP is that in order to form a neighborship, we have to statically configure the IP address of our neighbor. Here's how we do that. We're going to say neighbor, and I'm going to specify the IP address of router R2. At the other end of this link, on router R2's Fast Ethernet 0/0 interface, we have an IP address of 192.0.2.2. And as part of the neighbor statement, we say, in what autonomous system does this neighbor reside? And in this case, it's our autonomous system. We say remote AS 65001. This is the autonomous system of our neighbor. When we have a neighbor like this neighbor is said to be an IBGP neighbor. And IBGP, that stands for internal BGP. Normally, when we think about BGP, our neighbors are going to be EBGP, external BGP neighbors. But in this case, we have an IBGP neighbor. And while we're on that topic, I want you to know about a behavior that might cause an issue for you someday. It's not causing an issue in this topology, but let's imagine that we had another router connected off of R1, another router that was part of Autonomous System 65001. Let's say that I was specifying a neighbor of 10.1.1.2, and I had already said that its remote autonomous system was 65001. In other words, it's an IBGP neighbor. Here's what would happen by default. Let's say that I've learned about that 9.9.9.9/32 network from the internet, and I learned about it from router R2. When that network came into this autonomous system, it came into router R2. And router R2 advertised that network to R1, and R2 said that the next hop address to get to this network is me. It's R2. It's R2's IP address. Well, here's what happens with IBGP. Within an autonomous system, by default, that next hop address does not change from the time it came into the autonomous system. That means if R1 were advertising that network out to another neighbor in 65001, it would still be giving R2's IP address as the next hop IP address. And if that router did not know how to get back to router R2, then it would not know how to get to 9.9.9.9/32. A way to overcome that is to specify the next hop self option. After saying neighbor, I could say neighbor 10.1.1.2, and then I could say next hop self. Then when I advertised 9.9.9.9/32 out to this fictitious neighbor, router R1's IP address would be listed as the next hop. Just a little real-world tip for you. It's not relevant to this demonstration, but while we were on the topic of IBGP, I wanted you to know about that. Well, I think we're done on router R1. Let's go over to router R2 and do a similar configuration. We'll go into global configuration mode, and we'll say router BGP. We're still in Autonomous System 65001, and I'm going to statically set the BGP router ID to 2.2.2.2 in this case. Now I'm going to give a series of network commands to say what interfaces I want to participate in this BGP process. I'll say network. And for the 192.0.2.0 network, which is connected to Fast Ethernet 0/0, I'm using a classful mask, so there's no need to give the mask option. However, for network 198.51.100.0, I'm using a 30-bit subnet mask. In this case, I do need to say mask, and I give the subnet mask, 255.255.255.252. I'm going to give a similar network statement for the network connecting me over to ISP2. It's this network with a 30-bit mask. Now I need to specify my neighbors. we'll say neighbor, and one neighbor is router R1 with an IP address of 192.0.2.1. And the remote autonomous system, the remote AS, is actually my autonomous system. This is an IBGP connection. We say remote AS 65001. ISP1 is a neighbor. To specify that, we'll say neighbor 198.51.100.2. And it is in autonomous system 65002. One neighbor to go, we'll say neighbor 198.51.100.6. That's router ISP2. It's in autonomous system 65004. Oh, and did you notice that we had a neighborship form with ISP1? We should have a neighborship form with ISP2 in just a few moments. There it is. Oh, and also, we formed a neighborship with R1. Let's go back to router R1 now and make sure that we've learned all of these routes in our topology. I'll do a show IP route. And yes, indeed, I know how to get to this 9.9.9.9/32 network. That was representative of some network out on the internet. Can I ping it? Let's try to do a ping to 9.9.9.9. It's successful. Now that we've done that, in our next video, we're going to keep this same topology, this same configuration, and take a look at the output of some BGP show commands, some verification commands, and talk about how to interpret the output of those commands. I'll see you back for that video in just a moment. BGP maintains a couple of different data structures. There's a BGP neighbor table and a BGP table. And of course, there's a linkage between BGP acting as a routing protocol and our IP routing table. In this video, let's take a look at some BGP-specific show commands that will show us the contents of these different tables. First, what do we find in these tables? Well, the BGP neighbor table contains a listing of all of our BGP neighbors. And these neighbors, remember, have to be statically configured on our router. And this table is going to include that neighbor's IP address, their autonomous system number, and the current state of our neighborship. The BGP table is sometimes called the BGP RIB, the routing information base, because this table contains all routes known to BGP. And when BGP knows about a route in the BGP table, that route becomes a candidate to be injected into the IP routing table. However, just because the BGP table knows about a route, that's no guarantee that it will be injected into the IP routing table. One reason a route known to the BGP table might not show up in the IP routing table is there's a more believable source. Remember that we use administrative distance to determine which routing source is most authoritative. And EBGP, external BGP, has an administrative distance of 20. So that beats out OSPF, it beats out EIGRP. However, internal BGP, IBGP, it has a much higher administrative distance. It has an administrative distance of 200. However, directly connected networks, statically configured networks, they can certainly beat out external BGP by having a lower administrative distance. Another reason that a route in the BGP table might not appear in the IP routing table is the next hop address that shows up in the BGP table for a specific network. That next hop address might not be reachable based on the IP routing table. If the router cannot get to the next hop, then it's not going to inject that route into the IP routing table. Now let's take a look at some show commands. We're sitting here on router R2 and we're pretending that we're connected out to a couple of different ISPs. And if you take a look at the topology, I should have three neighbors. R1 should be a neighbor, ISP1 should be a neighbor, ISP2 should be a neighbor. Here's one way to get some information from the BGP neighbor table. I can do a show IP BGP summary command. What kind of information does this give us? Well, it shows my local BGP router ID, it shows my local autonomous system number, it shows how much memory that BGP is using, and if we're maintaining a full internet BGP table, that memory usage could be significant. But the main thing I normally use this command for is to take a look at my neighbors. And as we predicted, we have three neighbors. And we can see the autonomous system of each of those neighbors. They reside in these autonomous systems. And we can also see that we're actively talking with these neighbors. Notice we can see the prefixes received from the neighbors. I've received a prefix from all of my neighbors. I'm not in an idle state. That's good news. If I want even more details about my neighbors, I could say show IP BGP neighbors. And this is going to give me very detailed information about every neighbor. Here is my neighbor of R1. We see its autonomous system number. We see its router ID. We see counts for the BGP messages we have sent and received with that neighbor. Lots of detailed information about our neighbors. In fact, it's usually more than I need. I'll typically just do the show IP BGP summary command if I want to see my neighbors. Next, let's take a look at the contents of the BGP table. This is like the BGP routing table. To see the contents of the BGP table, we can do a show IP BGP. And notice that we have a collection of networks known to BGP. We also have next hop information, and this is what I was mentioning earlier. Let's say that to get to the 9.9.9.9/32 network, I could use this path or I could use this path, but if I'm unable to reach those IP addresses based on my IP routing table, then this network of 9.9.9.9/32, it will not be injected into the IP routing table. We also see values for our path attributes. That's going to be a big topic for our next module. Metric, local preference, weight, autonomous system path. In fact, let's talk right now about how to interpret this autonomous system path. You see a listing of autonomous systems, and we're saying to go to 9.9.9.9/32, here's my path. Here's what this is telling us. It says that to get to this network, if I used this next hop, then I would need to go through autonomous system 65004, and then I would need to go into autonomous system 65003. That is the autonomous system that contains 9.9.9.9/32. If I went via this next hop, I could go through autonomous system 65002, and then I would go into autonomous system 65003. If a network is local to my autonomous system, in fact, I'm connected to this network, notice that there are no autonomous system numbers listed in the path. And also notice that for some of these networks, we have more than one way of getting there. Again, consider 9.9.9.9/32. I could get there via a next hop of 198.51.100.6, or I could go via 198.51.100.2. If you take a look at the topology, you can see that I've got a higher bandwidth link out to ISP2. It would be preferable based on bandwidth to use this as my next hop. Well, which one am I using? Notice the greater than sign. The greater than sign indicates the best route. And right now, this greater than sign is indicating that 198.51.100.2, that's ISP1. It's indicating that that is the best route. That's a lower bandwidth link. Why are we using that? Because BGP does not consider bandwidth in its calculation. We've got a lot of ties here. We have no metric value for either path, no local preference, the weight is 0, and the autonomous system path length for each path is equal. And again, in the next module, we'll go through the decision-making process that BGP uses, but what this is coming down to is a tiebreaker of who has the lowest router ID. And because ISP1 has a lower router ID than ISP2, that's the path that we're using. And it's this best path that becomes a candidate to be injected into the IP routing table. Both of these routes are not going to show up. Let's take a look at the routes in the IP routing table that are there because they've been learned via BGP. To do that, we can say show IP route BGP. And we see that we've learned, for example, 9.9.9.9, and it's via a next hop of 198.51.100.2. That's ISP1. And in the next module, we're going to see how we can manipulate some of BGP's path attributes to start using the higher bandwidth link as we're going out to the internet and as traffic is coming back into us from the internet. But this video has been a look at the BGP data structures and how we can get information from those data structures. In this video, let's take a look at how a couple of routers can form a BGP neighborship and what messages are used to communicate between a couple of BGP neighbors. Remember that unlike OSPF or EIGRP, which usually will use multicast messages to dynamically discover a neighbor, BGP requires that we statically configure the IP address of a neighbor. And when we start out, before we've communicated with one another, we're in the idle state. R1 and R2, they're going to try to form a neighborship, but right now they are idle. And something that's somewhat unique to BGP is that it forms a TCP session between these two routers. That TCP session is set up in a connect state. Then, in our example, R1 sends an open message. That's one of 4 BGP message types we're going to be talking about in this video. R1 is sending an open message to R2, suggesting that they become neighbors. And inside of that open message, R1 is sending R2 information about itself. And I'll show you in just a few moments the specific information in an open message. In this example, R2 receives the open message from R1, and it sends an open message of its own back to R1. Now these routers can be in the open confirm state, but we're not fully a neighbor yet. You see, a BGP router is going to periodically send a keep alive message to its neighbor so that its neighbor knows that it's still there. And when we go into this open confirm state, yes, we have received an open message from our potential neighbor, but we're also waiting at this point for a keep alive. And if these routers send keep alives to one another, then we can go into the established state. Now we're ready to start exchanging route information. But what would have happened if one of these routers did not receive a keep alive message during that hold time? Well, in that case, the router would have sent a notification message and it would have returned back to the idle state. But in this case, we're assuming that each of the routers did receive a keep alive message and they moved into the established state. Now let's take a closer look at the 4 different types of messages that BGP uses. The first one, and we mentioned it earlier, is the open message. The open message is going to contain the version of BGP that we're speaking, and as of right now, that's going to be version 4. A router is going to send in an open message its local autonomous system number, not the autonomous system number of the potential neighbor, but its local autonomous system number. It's also going to send the hold time, the amount of time we'll wait for a keep alive. A router also includes its BGP router ID, and there could be some optional parameters. For example, if we're doing authentication, that would fall under the optional parameters category. We also talked about the keep alive message that was sent. This is a very lightweight message. It's just a message header, and it keeps the hold timer from expiring. It's a way for one router to tell its neighbor that it's still there. The message type that BGP uses to send routing information is called an update message. And this update message can have a listing of network prefixes that we want to withdraw from the BGP table, if we have any of those. The update message contains path attributes, such as the autonomous system path, the local preference, and also network layer reachability information about the network prefixes that we are advertising. And the other message type is a notification message. Remember we said that in the open confirm state, we had received an open message, but we were waiting for a keep alive to be received. If a keep alive had not been received, we would have sent a notification message. A notification message gets generated when there's some sort of an error. There's an error code, there's a subcode, and there's also some more detailed information about the error that's included in the notification message. And those are the 4 message types used by BGP: open, keep alive, update, and notification. BGP creates updates on a neighbor-by-neighbor basis, and if we have a lot more neighbors, that's going to require a lot more CPU resources on the part of our router. And if we do filtering, if we have something like an IP prefix list or a distribute list, and we apply that to several of our neighbors, that's going to increase the CPU demand even more. However, we might have a similar set of parameters configured for multiple neighbors. We might have the same IP prefix list configured for this neighbor and this neighbor and this other neighbor. And instead of using CPU resources to determine which routes we should be filtering from a neighbor or routes going to a neighbor, what if we said this select group of neighbors are all going to be using the same set of filters? And instead of using CPU resources on each individual neighbor, what if we group them together? That's what we can do with BGP. We can create something called a BGP peer group, and we can apply our filtering commands to the peer group as opposed to each individual neighbor. And then we can say that specific neighbors belong to this peer group, and that can, in a large-scale network, dramatically reduce the CPU demand on a router. Let's demonstrate it with this topology. Here we've got router R2 connecting out to ISP1 and ISP2, and let's say that, even though this is not a large-scale network, it will demonstrate the concept. Let's say that we want to make sure that we're not receiving private IP addresses from our ISPs, RFC 1918 addresses, because those networks are not supposed to be routed over the internet. That might be a security concern if we started receiving advertisements for the 10.network as an example. And I've already got an IP prefix list configured to filter out RFC 1918 addresses. Let me show it to you. Let's do a show IP prefix-list, and there it is. And I could go into BGP router configuration mode and say for the neighbor of ISP1, I want to apply this prefix list in the incoming direction. For ISP2, I want to apply this prefix list in the incoming direction. However, since we have the same prefix list that's going to be applied to 2 different neighbors, we can simply group those neighbors into a BGP peer group. Here's how that works. Let's go into BGP router configuration mode. We'll say router BGP, it's autonomous system 65001. And here's how we define, here's how we create a peer group. I'll say neighbor, and I'll call the peer group route-pg for peer group. And I'll say that this is a peer group. We just defined the route-pg peer group. Now we can apply this prefix list to the peer group as opposed to applying the prefix list to specific neighbors. To do that, we'll say neighbor, and the neighbor is route-pg, and we'll say prefix-list, and we'll apply the prefix list of, I called it route demo, And we'll apply that in the inbound direction. We're not wanting to learn RFC 1918 addresses from our neighbors. And we'll enter that. Now I've applied this filtering rule, the IP prefix list, to the peer group. However, as of right now, nobody belongs to the peer group. Now let's go in and say that ISP1 belongs to the peer group and ISP2 belongs to the peer group. Here's how we do that. We'll say neighbor, and I'll give the IP address for ISP1, 198.51.100.2, and I'll say it belongs to peer group route-PG. Let's do the same thing for 198.51.100.6. And you see confirmation on screen that these neighbors have been added to the peer group. Now, when BGP goes through its calculations about what routes to permit and what routes to filter, as advertisements are coming in, now we don't have to do it for each individual neighbor. We can just do it one time because these neighbors belong to the same peer group. When BGP makes its path selection decision, it can be a lot more involved than OSPF or EIGRP. OSPF can simply say, let's look at the bandwidth, calculate a metric using the Dijkstra shortest path first algorithm, and go with the lowest metric. EIGRP by default only considers bandwidth and delay. However, BGP can take several things into consideration, and I've got all of them listed here on the screen for you. This listing is comprehensive, and it's more than you might see in some documentation, because some of this deals with more advanced configuration like a route reflector or multipath BGP, things that we're not concerned with here at the CCNP level, but I wanted to give you a comprehensive listing and then tell you what's really most important to you and me on a day-to-day basis as we try to influence inbound and outbound path selections. But let's go through the complete listing first, just so that we've been exposed to that. And these are listed top to bottom in order of preference, and the first path selection parameter we have is a weight. This is a Cisco-specific parameter, and it's locally significant to a router. This does not get communicated to our neighbors. As a route comes into our router from a neighbor, we can stamp it with a weight. And we can say that routes coming in from one neighbor have this weight, routes coming in from another neighbor have a different weight, and a higher weighting is preferred. That's a really common way to influence our outbound path selection. We can go with the routes that have the higher weight that came in from a specific neighbor. Something that's not Cisco specific, but is commonly used for outbound routing decisions, is a local preference. With local preference, a higher value is preferred, and this value is not locally significant. It gets communicated to all the routers within a single autonomous system. Next, we're asking, from where did this network prefix originate? We're going to prefer a path or a route that was originally sourced from a network statement, or maybe a redistribute statement given in router configuration mode for BGP. Those are going to be preferred over a route that was injected by the aggregate address command. Next up is the AS path length. This is the number of autonomous systems that are in the AS path attribute. Remember, we saw that in our last module. It was a listing of autonomous systems that would allow us to get to a specific network prefix. And if I have two different ways to get to a network prefix, BGP can prefer the path that has the fewest number of autonomous system hops. Not router hops like RIP, but autonomous system hops. Next up is the origin type. How was the route injected into BGP? Was it injected from an IGP, an interior gateway protocol, an EGP, which would be BGP, or do we have incomplete information about that? Well, the origin type of an I is preferred to an E, and that's preferred to the question mark, incomplete information. Next up is the MED, the multi-exit discriminator. This is commonly used to influence inbound route selection. Maybe we're trying to influence routers out on the internet to come into our network via one ISP. What we're doing is setting this parameter on routers in one autonomous system, and that's to influence the BGP path selection made by routers in a different autonomous system, and a lower multi-exit discriminator is preferred. Next up is paths. We will prefer an EBGP path. Remember, that's a path between different autonomous systems over an IBGP path. That's a path within an autonomous system. Next up, we have a tiebreaker. If everything is a tie up to this point, we can look at the next top address for a network prefix and say, what is the lowest IGP metric? Maybe we're running OSPF as our interior gateway protocol. Which of these paths have maybe the lowest OSPF metric to get to this next top address, and we can go with that. Next up, we're asking a question. We're determining whether or not we're enabled for BGP multipath. Do we need to have multiple paths injected into the routing table? And if we've not yet selected a best path, then our interrogation of these parameters continues. The next tiebreaker we have is, which EBGP route is the oldest, and that oldest route is going to be preferred. If we still have a tie, we're going to go with the lowest router ID. Which neighbor has the lowest router ID? The next parameter isn't something that we really consider at the CCNP level. It deals with a route reflector BGP configuration, and if we do have that kind of configuration, we're going to prefer the route that has the minimum cluster list length. This isn't something we need to be concerned with for the route course, but I wanted you to be exposed to this comprehensive listing. And finally, the final tiebreaker is, which of my neighbors has the lowest IP address? That's going to be my preferred path. And if you count all these up, there were 13 different criteria that we examined. That's a lot. That's a lot to remember. And I've heard a variety of memory aids to help you remember specific path selection parameters. I wrote about one of these memory aids in the Route Official Certification Guide from Cisco Press. And if you happen to have that book, you might want to check out that memory aid. But here in this video, I wanted to share with you what I consider to be the simplest memory aid that I've come across. And it really does a nice job of helping us remember some of the key components in this BGP path selection decision. It's not totally comprehensive. It doesn't get into route reflector considerations, but it is useful the vast majority of the time. And by the way, I did not personally make up this memory aid. This is just one of the more popular memory aids that are out there, and I wanted to share it with you. It's an acrostic, and it goes like this. We love oranges, as oranges mean pure refreshment. Here's what that means. The W in wait corresponds to the W in we. We helps us remember wait. We love, the L is for the L in local preference. We love oranges. The O in oranges is from the O in originate. We love oranges as, and the as reminds us of the AS in autonomous system, the autonomous system path length. We love oranges as oranges. We have O for origin type, where I is preferred to E and E is preferred to question mark. We love oranges as oranges mean. The M in mean reminds us of the M in the MED, the multi-exit discriminator. The lower the MED, the better. We love oranges as oranges mean pure. The P in pure reminds us of the P in PAS. We prefer EBGP PAS over IBGP PAS. We love oranges as oranges mean pure refreshment. And we jump down to the router ID, the R in refreshment, reminding us of the R in router ID. This might be a simpler table for you to memorize. And it helps us remember again, we love oranges as oranges mean pure refreshment. However, this is still quite a listing. What do we as network engineers need to do typically to influence our routers going out to the internet and to influence routers on the internet as they come into us? Which service provider will they use as they come into our network? Really, it all boils down to 4 main path attributes that we can modify on our router. We probably cannot touch the service provider's router, but we can manipulate our routers and we can configure the wait, the local preference, the autonomous system path length, and the MED. And what we've got coming up next is a video on each of those path attributes. And we want to see in a live interface how we can use these path attributes to influence inbound or outbound BGP routing decisions. I'll see you in the next video where we'll take a look at the wait path attribute. In this video, we want to see how we can go into router R2 that's sitting at the boundary of our enterprise network, going out to a couple of different ISPs. We want to go into router R2 and see how to influence outbound path selection. We've got a couple of ISPs that can give us redundancy, but notice the bandwidth of the link going to ISP1 is 768 kilobits per second, while the bandwidth going to ISP2 is a T1 speed. It's 1.544 megabits per second. We would prefer to use ISP2. Which way are we going right now? Let's take a look at our BGP table and see right now how we're going out to a typical network on the internet. And we're pretending that 9.9.9.9/32 is representative of some network out on the internet. We'll do a show IP BGP, and you can see that we have a couple of ways to get to this network. We could get there via ISP2, we could get there via ISP1, but notice what we're doing right now. We're going via ISP1. The greater than sign indicates that this is the best route. Remember those decision-making criteria that we went through in the previous video? It looks like we have a lot of ties here. We have a tie for the wait, the local preference, the autonomous system path, the MED or the metric. It's probably coming down to which router has the lower router ID, which would be ISP1. We want to use the wait attribute, though, to try to go out via ISP2. And the wait attribute, recall, is a Cisco-specific parameter. It's not technically one of the BGP path attributes. It's locally significant to a router, The wait is not going to be communicated to any other routers. It's a way for one router to assign a preference to routes coming in from one neighbor versus another neighbor. Here's what we can do. Right now, notice that the wait is 0 for both of these paths. We can say that the path to ISP2 has a wait greater than 0, because with wait, higher is better. Let's set it to 10. And then we should see this greater than sign go from ISP1 to ISP2. That's what we want to achieve. Here's how we can assign the wait. We can create a very basic route map. I can say route-map. Let's give it a name of set-wait-10. And I'll say set wait 10. And we've created the route map. Now we need to go into BGP router configuration mode and apply that route map to routes coming in from ISP2. Let's go into router configuration mode for BGP Autonomous System 65001. And ISP2 has an IP address of 198.51.100.6. We'll say neighbor 198.51.100.6, and we'll apply the route map that we named set-wait-10. We're going to apply that in the inbound direction. In other words, we're receiving routes from this neighbor. We want to apply that route map and set waits on those routes learned from this neighbor. Let's press enter. And to make it take effect without being terribly disruptive to the BGP process, we can say clear IP BGP star. If we just pressed enter here, this would drop the TCP connections that we have with all of our neighbors, and that could be disruptive to a production network. I want to say clear IP BGP star soft. This is a soft reset. It's less disruptive to our network. Let's now do a show IP BGP to see what we're now preferring as the best route to get to 9.9.9.9/32. Now notice, to get to this network, the best route is indicated with the greater than sign. It points to ISP2. Why did it change? Look at this. The wait is now 10. It's greater than the wait, which is the default of 0, via ISP1. And what I'm going to do now is undo the configuration we just did, and then we'll come back in the next video and see how we can do something very similar, this time using the local preference attribute. But this video gave us a look at how we could use the Cisco proprietary wait attribute to influence outbound BGP route selection. In our last video, we saw how we could use the wait attribute to influence the outbound path selection from router R2 to these two different ISPs. We said that the wait attribute, though, was a Cisco proprietary attribute. It really didn't qualify as one of the BGP path attributes. And it was also locally significant to just one router. Let's take a look now at the local preference attribute. This is a BGP path attribute. It's not something that's Cisco specific. And instead of being locally significant, it's autonomous system specific. In other words, once we set this local preference value, it's communicated throughout an autonomous system. It helps routers in an autonomous system choose an appropriate exit point. And in this example, we want to do what we accomplished in the last example. We want R2 to choose ISP2 to get out to the internet, specifically to get to a typical network on the internet such as 9.9.9.9/32. If we do a show IP BGP to look at our BGP table now, we see that the greater than sign is indicating we're using ISP1, and that has a lower bandwidth than the path to ISP2. We want to use ISP2. Notice I got rid of the previous configuration. The waits are back to their default of 0, because now we want to take a look at a different way of accomplishing the same result. And that is, let's use ISP2 based on the local preference for ISP2 being higher. A higher local preference is preferred. Let's do this. Let's create a couple of route maps, one for ISP1 and one for ISP2, and let's assign a local preference to routes coming in from each ISP. First, I'll say route-map, and I'll call this ISP1. And let's set the local preference to a value of 50, we'll say. And we'll set the local preference going to ISP2 to a higher value. But for ISP1, let's say that the local preference is 50. Let's create another route map. Let's create one for ISP2. This time, let's set the local preference to 150. Higher is better. Now let's take these two route maps and apply them to our ISP1 and ISP2 neighbors. Let's go into router configuration mode for BGP Autonomous System 65,001. And for ISP1, we can say neighbor, and it has an IP address of 198.51.100.2. And I can say that I want to apply the route map called ISP1 in the inbound direction. We want to be marking routes coming in from ISP1 with a local preference of 50. We'll press enter for that. Now, let's set the route map for ISP2. ISP2 has an IP address of 198.51.100.6, and we'll use the route map of ISP2 in the inbound direction. And to make this take effect, we'll do a clear IP BGP star soft. We'll do a soft reset, and let's see if this has taken effect. Let's do a show IP BGP. Remember, just a moment ago, we were using ISP1 to get to the 9.9.9.9/32 network. What about now? Let's take a look. Now the greater than sign indicates that we're using ISP2. Excellent. Why is that? Well, it's not the weight, because the weight is equal, but the local preference is not equal. We've got a higher local preference for routes coming in and learn from ISP2 as compared to ISP1. This is another way that we can influence outbound path selection. What I'm going to do now is save this configuration. And in our next video, we're going to see how we can influence inbound path selection. A router out on the internet is trying to come into the enterprise. How do we make sure that we come in over the link that's using the highest bandwidth? And we're going to do that by manipulating the autonomous system path length. We'll see you back for that in just a moment. In our previous two videos, we've been taking a look at how we could go to R2 and influence outbound path selection, going out to the internet. However, when we have traffic coming in from the internet, we would probably prefer that that traffic use the higher speed link coming into our site. And we are probably not going to be able to do any configuration on the ISP routers. We're going to have to control that inbound path selection from our router. How do we do that? Let's consider this example on screen. If we go to ISP1, and we do a show IP BGP, let's see what path we're going to use to get to one of the interior networks inside of Autonomous System 65,001. How do we get to 192.0.2.0/24? We've got a couple of paths. We could go via this INET router, which is then going to go to ISP2, and that's then going to go into our autonomous system, or we could go directly into our autonomous system. From the perspective of ISP1, we have an equal weight and a local preference and a MED, but the autonomous system path length, that's the tiebreaker in this case. Notice that we're preferring to go directly into our autonomous system because it's only one autonomous system hop. We're going directly into 65,001. Even though we might have much higher bandwidth going from ISP1 to INET to ISP2 and then in to our autonomous system. But look at all the autonomous system hops. We would have to go through 65,003, then we would have to go through 65,004, and then finally we go into 65,001. But let's imagine we want to use that path. Let's imagine that between these internet service providers, they have plenty of bandwidth. We would much rather use that path, even though it's more autonomous system hops. How do we make that happen? One strategy that we can do from our router is to do an autonomous system path prepend. Let me show you how this works. Let's go into router R2 and let's create another route map. I'll say route-map and let's call it long AS path. And I'm going to set the autonomous system path prepend value. In other words, this is the value that I'm going to stick in front of the autonomous system path that I'm advertising out to a neighbor. I'm going to say that I want to prepend to that autonomous system path 3 additional instances of my local autonomous system. I'm going to say 65,001, 65,001, and 65,001. Now, if I go into router BGP configuration mode for 65,001, I can say when I'm sending advertisements to ISP1, I want to prepend the autonomous system path with 3 instances of my autonomous system. That's going to make those routes less desirable to ISP1. They're going to appear to be even more autonomous system hops than going from ISP1 to INET to ISP2 and then into our autonomous system. Let's apply this to our ISP1 neighbor. I'll say neighbor, and we'll give the IP address of 198.51.100.2, and I'll say that I want to apply the route map that we named long AS path. And I want to do this in the outbound direction when I'm sending advertisements to ISP1. That's where I want to do it. To make this take effect, let's do a clear IP BGP star soft. Then let's go back over to ISP1 and see if this change has taken effect. We'll give it a few seconds. And let's do a show IP BGP. Remember that previously the preferred route was to go directly to R2 because it was only one autonomous system hop. Now, however, to get to 192.0.2.0, the preferred path is via 203.0.113.2. That's INET, which is then going to go to ISP2, which is then going to go into R2. The reason is the path directly into our autonomous system to 198.51.100.1, it doesn't appear to be direct, does it? Look at this autonomous system path. It looks like we have to go through autonomous system 65,001, and then we have to go through autonomous system 65,001, and then we have to go through autonomous system 65,001, and finally we go into autonomous system 65,001. Wow, 4 autonomous system hops as compared to going to the INET router, which is 3 hops. We go through 65,003, we go through 65,004, and then into 65,001. Using the autonomous system path prepend feature, we've now, on our local router inside of our enterprise, we've been able to influence how the internet sees our network, and we've influenced that incoming traffic to use the faster link coming into our enterprise. Notice that I've added a link between router R2 and our autonomous system, the enterprise autonomous system, and ISP1 and the ISP1 autonomous system. And now that we have these 2 links interconnecting these autonomous systems, we probably want to use the link that has the highest bandwidth. That's the newly added link between R2 and ISP1. However, let's see what's being used right now. On ISP1, if I do a show IP BGP, and I'm trying to get to a network inside of our autonomous system, like 192.0.2.0. How am I getting there currently? Well, currently, I'm using this link, and this is the 768K link. However, I've got this newly added link that's not being used. This is the T1 link running at 1.544 megabits per second. We know that we're using the 768K link because of this greater than sign indicating that this is currently the best route. What we want to do is to influence the ISP1 autonomous system to send traffic into our network using this as its next hop. And a path attribute we can use to do that is called the MED, the multi-exit discriminator. And the MED is useful between a couple of autonomous systems. What we're going to do is create a couple of route maps. And these route maps are going to set different MED values. And with MED, lower is better. And I'm going to apply the route map with the lower MED value to the neighboring IP address across the T1 link. And I'll apply the route map with the higher MED value to the neighboring IP address across the 768K link. But this MED value is only going to be used between these 2 autonomous systems. I'm going to be marking routes coming from my autonomous system, 65,001. I'm going to be marking those routes with these different MED values and sending those into autonomous system 65,002. However, it doesn't go beyond there. 65,002 is not going to advertise those MED values to any other autonomous system. It's only between these 2 autonomous systems. It's a way for one autonomous system, like an enterprise network, to influence a neighboring autonomous system, like their service provider, to use a particular link when we have 2 or more links interconnecting those autonomous systems. Let's go over to router R2 because we're not going to be allowed to configure anything on ISP1. We need to control things from our router. And let's go into global configuration mode and create a couple of route maps. We'll say route-map, and let's call one MED 10, and let's set the metric to 10. And metric is the same as MED. When you see the metric column in the output of the show IP BGP command, that's talking about the multi-exit discriminator, or the MED. Let's create another route map called MED 20, and here we'll set the metric, or the MED, to 20. Now that I've got the route maps created, let's apply those route maps to our neighborships on ISP1. We'll go into router configuration mode for BGP Autonomous System 65,001, and we'll say neighbor. And for the 768K link, the IP address at the far side of that link is 198.51.100.2. And let's apply the route map called MED 20. That's the route map with the higher metric value. Remember, with MED, lower is better. And let's apply that in the outgoing direction to networks that we're advertising into that autonomous system. Let's give another neighbor statement. The neighboring IP address across the T1 link is 198.51.100.10, and we'll apply the MED10 route map. It's going to be a lower value. And to make this take effect, let's do a clear IP BGP star soft. And we'll wait a few seconds for this to take effect. And then let's go over to router ISP1. And remember, just a few moments ago, we were preferring to use the 768K link. We want to use this link, however. Let's see if things have changed. Let's do a show IP BGP. And this time, to get to the 192.0.2.0 network, look at this. The best route is via that T1 link. Excellent. And we can see why. You see the metric column? This shows the MED values. By the way, the default MED value is 0, so we could have left the MED value at its default setting for our preferred route. That would have been an option. But here we can see that these two links on ISP1 have MED values or metric values assigned. The 768K link has a MED of 20 assigned, and the T1 link has a MED of 10 assigned. And with the MED, lower is better, and that's the reason that ISP1 is now choosing to come into our enterprise network using that newly added T1 link. This video takes a look at authenticating BGP sessions between a couple of routers. Again, we're going to use routers R1 and R2. Notice that they're in different BGP autonomous systems. But before we get into the configuration aspect, let's think about the likelihood of something like this happening. After all, OSPF, EIGRP, they can use multicasting to dynamically form neighbors. And as a result, in many instances, it's not a big challenge to insert a router into a network and have that router start peering with existing production routers. And if that's a malicious user that inserted the router into the network, they could start corrupting routing tables, which is one of the big reasons we've been spending a lot of time in previous videos seeing how to authenticate OSPF and EIGRP sessions. But BGP is a bit of a different story. With BGP, we're not dynamically discovering our neighbors. With BGP, we have to go in and statically configure the IP address for a neighbor. And because of that, it seems a lot less likely that somebody would maliciously introduce a router into the network and be able to establish an unwanted BGP session with the production router. However, there is a way. An attacker might use an attack called session hijacking. You see, BGP is TCP based, and sometimes attackers are able to hijack an existing TCP session. What if they hijacked an existing TCP session between a couple of BGP neighbors? They might be able to do that and have their router step into this TCP session that was already established, and as a result appear as a BGP neighbor to a production router, and then they could go about their business of corrupting routing tables. And because of a threat like this, it's a good idea to authenticate our BGP peers. There's not a lot to the configuration. It's not as complex as most of our previous configurations. It's one single command on each router. And we set things up exactly the same for both IP version 4 and IP version 6 networks. So we're not going to have separate videos showing you how to do it with IPv4 and how to do it with IPv6 because it's identical. Let's go ahead and set it up right now on this IP version 4 network. On router R1, let's go into router configuration mode for BGP autonomous system 65001, and the command that enables authentication is this. We say neighbor, and we give our neighbor's IP address. It's 10.1.1.2 from the perspective of R1, and we can give a password or a key here, and the type of authentication that's going to be used is MD5 hashing. We don't have the option for SHA, we don't have the option for plain text. The one and only option we have is MD5. And I'll say that my key is, I'll say key note. And if we waited long enough, we would see that the BGP session would be torn down because one neighbor has a key and the other one doesn't. But let's speed things up. Let's do a clear IP BGP star. And this is going to clear BGP. It's going to reset it. And notice that we're getting bad authentication messages. It says no MD5 digest exists from the other side. Let's fix that. Let's go to router R2 and let's set up an authentication key. Let's go into router configuration mode for BGP autonomous system 65002. And we're going to be pointing to our neighbor IP address of 10.1.1.1. And we want to give a matching password, a matching key of key note. And again, we'll speed things up by saying clear IP BGP. And let's see if we're now able to form a neighborship after we have matching keys on both sides. And look at this. It says that our adjacency is up. It says this neighbor is up. We can confirm that with a show IP BGP summary command, we can see that we do have a neighbor that is currently up. And it's interesting that we don't have a authentication specific BGP verification command we can give, but we can check to see whether or not we have a neighborship or not. And if we don't, then we might start troubleshooting authentication. And in this video, we've set up MD5 authentication for a BGP network that's using IP version 4, but the syntax and the configuration mode is identical for IP version 6. We're still in router configuration mode for our BGP autonomous system. And we still say neighbor, we still give the neighbor IP address, except it's an IP version 6 address. We say password, and then we give the key value. And this allows us to do MD5 authentication between a couple of BGP speaking routers.